Hello everyone, this is Dr. SUMIT CHAUHAN and today we'll discuss about network layer. Talking about the position of the network layer, it is the third layer from the bottom, and transport layer gives the data to the network layer, and network layer transfers the data to data link layer at the receiver end, whereas it receives the data from data link layer and transfers the data to transport layer. It has the responsibility of node to node delivery. Responsibilities of network layer: internetworking, addressing, routing, packetizing, and fragmenting. Now, two classes of service provided by the network layer. We have connectionless, we have connection oriented. Talking about routing, if connectionless service is offered, packets are injected into the subnet individually and routed independently of each other. No advanced setup is needed. In this context, the packets are frequently called datagrams and the subnet is called datagram subnet. Now here is an example of routing within a datagram subnet. We have A is table, which is initially has been shown that this is the initial table and this is a later stage table. Then we have C's table and we do have E's table. If connection oriented is used, a path from the source to the destination router must be established before any data packets can be sent. This connection is called virtual circuit. Now here you can see this is basically connection oriented. We are talking about a dedicated path, a virtual connection, a virtual circuit subnet is there in this route. Now to differentiate between virtual circuit and datagram type of routing, in case of virtual circuit, a session is established between source and destination. At the beginning of the session, route is decided for all the packets to be sent for that session. In datagram type of routing, each packet is independently routed. Now here we have the comparison of virtual circuit and datagram subnet. Circuit setup in datagram is not required, not needed. We required in virtual circuit. Addressing: each packet contains the full source and destination address because each packet is independent. They can go from any route whichever they want to, whereas in virtual circuit each packet contains a short VC number because they follow the same route. All packets follow the same route. So then we have state information, then routing, effect of routers failures, quality of service, and congestion control. Now talking about the different routing algorithms that we have, the optimality principle, we have shortest path routing, flooding, distance vector routing, link state routing, hierarchical routing, broadcast routing, multicast routing, routing for mobile hosts, and routing in ad hoc networks. The main function of the network layer is routing packets from the source machine to the destination machine. The algorithm that choose the routes and the data structures that they use are a major area of the network layer design. The routing algorithm is that part of the network layer software responsible for deciding which output line an incoming packet should be terminated on. If the subnet uses datagrams internally, this decision must be made anew for arriving packet since the best route may have changed since last time. If the subnet uses virtual circuits internally, routing decisions are made only when a new virtual circuit is being set up. Therefore, data packets just follow the previously established routes. This case is sometimes called session routing because a route remains in force for an entire user session. Routing algorithms can be grouped into two major classes. One is non-adaptive, the another one is adaptive. Now, non-adaptive algorithms do not base their routing decisions on measurements or estimates of the current traffic and topology. This procedure is sometimes called static routing. Adaptive algorithms, in contrast, change their routing decisions to reflect changes in the topology and usually the traffic as well. Now, list out the advantages and disadvantages of routing algorithms. We have fixed routing. The advantages of fixed routing are as follows. The routes are always fixed and hence the routing overhead is minimum. The routing is dependent on network topology, static in nature. Routing is same for datagram and virtual circuit type of services. And major disadvantages are lack of flexibility. The system is not robust. In case of link failure or node failure, the system cannot recover. And congestion may occur on a particular route. Talking about flooding and why flooding technique is not commonly used for routing. Now, flooding is one type of non-adaptive routing technique where no network information is used. In case of flooding, as each node receives a packet, it is retransmitted or forwarded to all the links connected to the node, except the link through which the packet has arrived. Flooding is not commonly used for routing for following reasons. Flooding leads to unbounded number of packets, may lead to congestion in the network, and number of copies of the same packet is delivered at the destination node. And defining autonomous system, a routing domain generally is considered a portion of an internet under common administrative authority that is regulated by a particular set of administrative guidelines. Routing domains are also called autonomous systems. Next we have link state algorithm and distance vector algorithm. Link state algorithm are also known as shortest path first algorithms. Flood routing information to all nodes in the internetwork. Each router, however, sends only the portion of the routing table that describes the state of its own links. In link state algorithms, each router builds a picture of the entire network in its routing tables. Then we have distance vector algorithms, also known as Bellman-Ford. Call for each router to send all or some portion of its routing table, but only to its neighbors. In essence, link state algorithms send small updates everywhere, while distance vector algorithms send larger updates only to the neighboring routers. Distance vector algorithms know only about their neighbors. Shortest path routing. In this picture, the first 5 steps used in computing the shortest path from A to D. The arrows indicate the working node. Distance vector routing algorithms operate by having each router maintain a table, that is a vector, giving the best known distance to each destination and which line to use to there. These tables are updated by exchanging information with the neighbors. The distance vector routing algorithms is sometimes called by other names. Most commonly the distribute Bellman-Ford routing algorithm and the Ford-Fulkerson algorithm. Distance vector routing. In distance vector routing, each router maintains a routing table index and containing only entry for each router in the subnet. This entry contains two parts: the preferred outgoing line to use for that destination and an estimate of the time or distance to that destination. The metric used might be number of hops, time delay in milliseconds, total number of packets queued along the path, or something similar. Each node constructs a one-dimensional array containing the distances to all other nodes and distributes that vector to its immediate neighbors. The starting assumption for distance vector routing is that each node knows the cost of the link to each of its directly connected neighbors. a link that is down is assigned an infinite cost. Here we have the pictorial representation of distance vector routing. From A to B, the cost is 1. From A to C, again the cost is 1. A to E, the cost is 1. A to F, the cost is 1. F to G, the cost is 1. And G to D, the cost is 1. Now, by using the information that has been stored at node, so we'll try to search out that what information has been stored at node A. So from A to A the distance is 0, for A to B the distance is 1, for A to C the distance is 1, A to D is not defined, A to E is 1, A to F is 1, and A to G is not given, right? So then we have B to A is 1, B to B is 0, B to C is 1, B to D is not given, B to E is not given, B to F is not given, and B to G is not given. And similarly so on. Now these are the initial distances stored at each node, and this is a global view. Now note that each node only knows the information in one row of the table. Every node sends a message to its directly connected neighbors containing its personal list of distance. For example, A sends its information to its neighbors B, C, E, F. If any of the recipients of the information from A find that A is advertising a path shorter than the one they currently know about, they update their list to give the new path length. And note that they should send packets for that destination through A. Node B learns from A that node E can be reached out at a cost of 1. B also knows it can reach A at a cost of 1, so it adds these to get the cost of reaching E by means of A. B records that it can reach E at a cost of 2 by going through A. After every node has exchanged a few updates with its directly connected neighbors, all nodes will know the least cost path to all other nodes. In addition to updating their list of distances, when they receive updates, the nodes need to keep track of which node told them about the path that they used to calculate the cost. So they can create their forwarding table, and the table will look like this. They'll say A to A is 0, A to B is 1, A to C is 1. Right? A to D is 2, A to E is 1, A to F is 1, A to G is 2. So we have again B to A is 1, B to B is 0, B to C is 1, B to D is 2 because B to A is 1 and A to D is 2. Now with the help of the previous table, we'll be able to calculate the cost and the next hop through which we can reach that node. Now here we have an example. We have a subnet input from AIHK and the new routing table for J. We use the same concept that we have discussed in the last 4-5 slides to calculate the new estimated delay from J. Now this is the count to infinity problem that we have in distance vector routing. Initially every system from A to A is down. After 1 second, B got to know that A is up. After 2 seconds, C got to know that A is up now. After 3 seconds, D got to know that A is up now. And after 4 seconds or 4 exchanges, E got to know now A is up. Now A is up at the right hand side, A, B, C, D, E. Now A gets down. Now B says that through C, it will get the information that C says that it can reach A by 2 and B can now reach A through C. So it will make an entry of 3. Now, in the next exchange, when C sees that the cost or the distance from B to A is 3 and he has to reach A through B only, so it will add 1 to that 3 and make changes in its table. And similarly, we have this exchanges, and on the basis of these exchanges they keep on exchanging their values depending upon the neighbor's value, and that's why this is called count to infinity problem. Link state routing, every node knows how to reach its directly connected neighbors, and if we make sure that the totality of this knowledge is disseminated to every node, then every node will have enough knowledge of the network to determine correct routes to any destination. Reliable flooding is the process of making sure that all the nodes participating in the routing protocol get a copy of the link state information from all other nodes. As the term flooding suggests, the basic idea is for node to send its link state information out on all of its directly connected links, with each node that receives this information forwarding it out on all of its link. This process continues until the information has reached all the nodes in the network. Link state packet contains the following information: the ID of the node that created the LSP, a list of directly connected neighbors of that node with the cost of the link to each one, a sequence number, a time to live for this packet. Flooding works in the following way: when a node X receives a copy of an LSP that originated at some other node Y, it checks to see if it has already stored a copy of an LSP from Y. If not, it stores the LSP. If it already has a copy, it compares the sequence numbers. If the new LSP has a larger sequence number, it is assumed to be more recent, and the LSP is stored, replacing the old one. The new LSP is then forwarded on to all neighbors of X except the neighbor from which the LSP was just received. Each router must do the following: discover its neighbors, learn their network address, measure the delay or cost to each of its neighbors, construct a packet telling all it has just learned, send this packet to all other routers, compute the shortest path to every other router. Now here we have an example. So first of all, we'll make a tree out of it. Now I'll measure the cost, measuring line cost, a subnet in which east and west parts are connected by two lines. Now building link state packets, we have packet number, name, A, sequence, age, and neighbor and the distance related to that neighbor. Distributing the link state packet, the packet buffer for router B in the previous slide, and here we have the updated ones. We have something send flags, acknowledgement flags. Hierarchical routing. When hierarchical routing is used, the routers are divided into what we call regions, with each router knowing all the details about how to route packets to destinations within own region, but knowing nothing about the internal structure of other regions. When different networks are interconnected, it is natural to regard each one as a separate region in order to free the routers in one network from having to know the topological structure of other ones. For huge networks, a two-level hierarchy may be insufficient. It may be necessary to group the regions into clusters, the clusters into zones, and the zones into groups, and so on. Now here we have an example of hierarchical routing. We have a full table of 1A we have the destination, all other indexes, we have the line through which we'll go there, and then we have hopes, means the number of nodes in between. Then we have a hierarchical table for 1A even, that we are only talking about the neighbors that we have, and then the region. Broadcast routing, we have a reverse path forwarding, a subnet, a sync tree, the tree built by reverse path forwarding. Broadcast routing, in some application, hosts need to send messages to many or all other hosts. For example, a service distributing weather reports, stock market updates, or live radio programs. Sending a packet to all destinations simultaneously is called broadcasting. Various methods have been proposed for doing it. One broadcasting method that requires no special features from the subnet is for the source to simply send a distinct packet to each destination. Not only is the method wasteful of bandwidth, but it also requires the source to have a complete list of all destinations. In practice, this may be the only possibility, but it is the least desirable of the methods. Flooding is another method. Another flooding is ill-suited for ordinary point-to-point communication. For broadcasting, it might rate serious consideration. The problem with flooding as a broadcast technique is the same problem. It has a point-to-point routing algorithms. It generates too many packets and consumes too much bandwidth. A third algorithm is multi-destination routing. If this method is used, each packet contains either a list of destinations or a bitmap indicating the desired destination. When a packet arrives at a router, the router checks all the destinations to determine the set of output lines what will be needed. The router generates a new copy of the packet for each output line to be used and includes in each packet only those destinations that are to use the line. Fourth broadcast algorithm makes explicit use of the sync tree for the router initiating the broadcast or any other convenient spanning tree for that matter. A spanning subtree is a subset of the subnet that includes all the router but contains no loops. If each router knows which of its lines belong to the spanning tree lines except the one copy of an incoming broadcast packet onto all the spanning tree lines except the one is arrived on. This method makes excellent use of bandwidth, generating the absolute minimum number of packets necessary to do the job. Our last broadcast algorithm is an attempt to approximate the behavior of the previous one. The idea is called reverse path forwarding. It's remarkably simple once it has been pointed out. When a broadcast packet arrives at a router, the router checks to see if the packet arrived onto the line that is normally used for sending broadcast packet to the source of the broadcast. If so, there is an excellent chance that the broadcast packet itself followed the best route from the router and is therefore the first copy to arrive the router. This being the case, the router forwards copy of it onto all lines except the one it arrived on. Now this is an example of mixed routing. Now routing with mobile hosts. A LAN to which LANs, MANs and wireless cells are attached. We have a wireless cell, we have a home agent, we have a foreign agent. Now here we have a packet is sent to the mobile host home address whenever you are on the roaming, right? So that's the first thing. Then packet is tunneled to the foreign agent back. Sender is given foreign agent's address, and then subsequent packets are tunneled to the foreign agent. Now, this is how routing for mobile hosts. Thanks for watching.